We are going to cover two topics of machine learning, model estimation and feature selection. Feature selection is also called variable selection. Its objective is to select relevant features to be used in model construction. Model estimation or model assessment is used to validate a chosen model among all possible models, making sure it fits the problem well. For both subjects, the best choice depends also on the industry you are applying it to. In our case, the focus is on credit scoring industry. The two are very related topics, as a model selected for a problem can have an impact on what features are selected, but the selected features can also guide a modeler to choose the most appropriate model. For the sake of this presentation, we will explain selecting features first, then move on to building models with the selected features. The best model is not always the most complicated. In fact, you might even reduce the accuracy of prediction by using variables that are not important, using too many of them, or even selecting them by intuition. To solve this issue, we are going to cover feature selection. This video contains information about forward, backward, stepwise, and genetic algorithm. First of all, let's start with the forward model. This model should be used when there is some important multicollinearity in your dataset. The concept is the following. You begin with no variables in your model, then you select the variable with the highest significance, r squared in our case. After that, you recalculate all the r squared with the variables currently in your model and all the rest of available variables. The best combination with the higher r squared is then added to the model, and so long as they improve the model. This is why it is a step-up method. To better visualize, I created 5 features with numbers ranging from 1 to 5. So first, you select the feature with the higher r squared value, which is feature number 2. Then, let's say the combination with the higher r squared is feature number 2 with number 4. So we now have 2 features in our model, 2 and 4. We now look again for the best combination of features in our model, composed of 2 and 4, with other features. The best combination is found with number 1, and so on. Next method for feature selection is backward. One example of use case can be having more observations than variables. Comparing to forward, the backward model starts the other way around. It starts with all variables included in the model, and at each step, the least significant variable in the combination of features is removed. And this goes on up to every non-significant variable is removed. In my example, the least significant features in our combination is number 4. Therefore, it's going to be removed. The new lowest is now number 3, so same thing, we removed it. As I set my significance level to 0.1, the other features are above it, so I don't need to go any further. My final features selected are number 1, 2, and 5. Stepwise now. Stepwise is pretty good to find best predicator variables in a dataset composed of independent variables. However, it is not advised to use stepwise when you have excessive collinearity, otherwise you might end up with an inconsistent model. Now I am going to cover forward stepwise selection. So every time a variable is added to the model, it checks all candidate variables in the model to see if their significance is now under the specified tolerance level. Should a variable become non-significant, it is then removed from the model. As you can see, it makes sure that added features are staying relevant through the many iterations. I described here a forward stepwise because I say added to the model, but a backward stepwise also exists, and you just have to replace the word added with removed. To summarize, each method is subject to different limitations. Therefore, you have to experiment to know which one is the best in your case. Stepwise is a standard in the credit scoring industry. Its limitation is that it doesn't consider dynamic interaction between variables. Genetic algorithm overcomes that, and we're going to see that later in the presentation. We are now going to see an example with Python. To quickly talk about the dataset selected, it comes from a Kaggle competition about credit scoring and has 11 features. The model we want to test on is linear regression. You can find the code on the following URL. We are trying to do a forward stepwise, using the residual sum of squares, or RSS, to select features. On the left side, you can see a chunk of code with the time needed to process different models based on the number of predictors we want. On the right side, we access more information about model. Then we know such thing as the r-squared value or the predictor used. To have the best model, you just bring the top model based on the higher RSS value we saw earlier. Now let's talk about genetic algorithm. This optimization technique is used to solve non-linear and non-differentiable optimization problems. It uses concepts of evolutionary biology to search for a global minimum to an optimization problem by imitating evolutionary biology techniques. You have 2 main steps. First, you make an initial generation of candidate solutions that are tested against the objective function. Then you generate subsequent generation of points from the first generation through techniques like selection, crossover, and mutation. First technique is selection. These parents are from the previous generation. Basically, they perform well, so we are keeping them. Crossover now. We select common similarities between the parent variables. We then decide to create children variables that will be in the next generation. Mutation. We take parent variables, mutate them, and create child variables. Mutation is interesting because it allows genetic algorithm to do some exploring without avoiding to fall into a local minima. Now let's see an example of genetic algorithm. It will help you to understand the process. Red and green minima are local minima, while the blue one is a global minima. So we want to find the blue one without getting trapped by the two others. The yellow small dots that you can see everywhere are initial points, the first generation of genetic algorithm. It then selects some good solutions, represented in green, as the parents to be part of the next generation. They will be used to create the other generations. We are now in the second iteration and generate new points in yellow. They are generated through selection, crossover, and mutation techniques. We evaluate the new population and then repeat iteration until the algorithm converges. Here, the green dot is in the center of the blue minima, meaning it found the global minima, and not local one. What are the advantages and disadvantages of genetic algorithm? It is good to find alternate solutions that would not be so obvious, like to find the global minima. Concerning disadvantages, it might be slower than other method, and it suffers from a lack of transparency because it is a simple method to implement, but difficult to understand. Furthermore, it can lead to some overfitting. And finally, mutation can be destructive if they don't go in the right direction. We are starting to see uses of genetic algorithm in the credit scoring industry as the industry moves toward better data science approaches. It has proved performance improvement over forward, backward, and stepwise selection.
Now that we have selected the features, let's go